Hello and welcome to another video from our BeamTool tutorial video series. In this video, we want to work together to make a scan plan for phase array inspection of a double V weld in a flat plate. The example that we're going to go with is a 25mm thick piece with a symmetric double V weld with 30-degree bevels and a landing of 2mm. And we're going to start from building the scan plan from scratch. So first of all, we open a new workspace, and the first step, we start with the piece. So here we are gonna inspect the carbon steel piece. So as a default, which is a default material for BeamTool, and we don't need to then change any the velocity, either shear or compression. The thickness is what we can change to 25mm for our example, and we don't need to change the length or width of the plate. After we set our piece, then we move to the Weld tab, and here is where we define the dimension of our weld. We come to the options that we have here, and we are going to deal with the double V with the landing. So this is the first option we choose. It is going to be a symmetric weld. If it was not symmetric, we could choose a symmetric option here that would give us a chance to define a symmetric weld. But in this case, we keep it as a default symmetric weld. And for having a 30-degree bevels, we change the parameters to match 30-degree at top fill, at the root fill. Then for the root face or the landing, we set the gap to 0, a landing size to 2mm, and to make these more basically like a same size from the top and bottom bevel, we change the height to 11.5. Now, what we can do to make sure all the dimensions are, we input all the dimensions the way we like, is that we can click show dimensions, and BeamTool will show all the dimensions of these bevels and landing and heights as we specified. Also for this example, we want to stick the has to 4mm, which is shown by the gray area parallel to the weld bevel. Now, in this case, if we leave the weld this way, we are going to ignore the presence of the weld caps. But if you want to add the cap, we can choose option here to add a cap on the top and also add a cap at the bottom. And then when we go to each of these, we can specify what kind of overlap and what kind of height we want. For this example, I just want to choose 3mm height and 5mm overlap. That be slightly longer than after the has. I will do the same for the bottom bevel. So at this point that we know that the weld dimensions are specified correctly, we can unclick show dimension and go to our main view. Now at this point we have our piece and the weld defined it correctly, and the next step would be to go and choose a phase array option from the probe. When you choose a phase array option, BeamTool will put on a phase array probe and wedge by default, and now there is a window here that gives all the parameters and with respect to positioning of this wedge. If you move this back and forth, this would be how the front of the wedge changes with respect to weld center. And then we can, for certain applications, we can move the probe up and down. In this scenario, we're going to be exactly on top surf, and these other ones that can tilt the wedge up and down that we are not going to use for this example, but you will see the examples of using these in our other videos. When we click on this button here, the view that we get here would be sharing information of the details of the wedge and probe. And by default, the probe is a 5 MHz probe, 64 element with pitch 0.6, and the wedge dimensions are all the dimensions of this wedge are all listed here in terms of its height, its angle, the velocity, all are specified here. Now, the first step would be for us to choose what probe and wedge we want to use for this scan plan or for our inspection. And this is where people generally refer to what they have in their inventory, or if they have a specific idea before making scan plan of what type of probe and wedge would be appropriate. For this example, I want to demonstrate the use of a common 64 element probe, 5 megahertz A12 from Evident, that it is basically a 5 megahertz 64 element and 0.6. And since I used this probe before, you notice that I have it on my workspace as a probe that I used before. If you are using a probe that it's custom, you can always define the parameters directly here, or you can use importing from catalog, that then most of the common probes from different manufacturers are listed here. So if you, for instance, for the same probe that I just showed, I can choose manufacturer to be Evident and then give as a part number, I can type, for instance, A12, and you see that all these common probes come there, that 5L64A12 is actually the one that I use here. Same thing for the wedge. If you have in your history, it's available, or we can import directly from the catalog, which again, in this case, I know that SA12 from Evident is the good wedge. So I'm going to go and try to find the one with a 55 degree, basically 55 degree nominal shear angle. And I choose that. And this will be the probe and wedge that I chose. Now, the next step then would be to actually actually choose the beam sets that we want to cover the bevels. So typically in different codes, we have options, or there are instructions of what type of angle we need to hit the bevels with. There are certain codes like ISO that they ask to hit the bevels with angles plus minus 6, or there are some AWS code that asks for plus minus 10. And I'm going to demonstrate here for this example aiming to inspect the bevels with plus minus 10 degree angles. So in this case, we say add the beam set, and these are all the beam sets we have options: single beam set, linear beam set, sectorial, compound scan. That we briefly explained these and their differences and options with regard to them in previous videos. Here, I'm gonna use a sectorial beam set for this demonstration. So first, I want to cover the bottom bevel. And when you choose a sectorial, it is a beam set that is generated by a fixed aperture. The window specific for the sectorial beam set gives us all the options that we can choose to define this beam set. Specifically, what is the start element and what's the aperture that's going to generate those beams, and what is the minimum and maximum angles that we want to be generated. Again, for this example, since we have a 30 degree bevel, normal to that would be 60 degree. And if you're going to go plus minus 10 from that, I want to choose the angles that the minimum angle be 50 and the maximum be 70, as it is here. I have a choice to choose what number of beams I want between the min and max and what deviation. I like to use 0.5 degree increments, and that gives me 41 beams. Now, to make sure that I cover the bottom bevel, I want to make sure that I can either move my wedge closer to the piece by moving like this, or move my aperture that creating these beams higher so that I can cover the bottom bevel. Here, we have an option to display the elements that are actually generating the beam set. In this case, if I increase the start element and go to use the last 16 element of the aperture, I would be in a better position to cover the bottom bevel with the current offset that I have. Here you will notice that now in the first leg, by the sectorial beam generated by the last 16 element, we have covered the bottom bevel and has an slightly left from the landing. So I may choose to just get a little bit closer so that I ensure that with my lowest angle, I cover my has, and my highest angle cover the top of my landing. And that would be the choice that I have. If in this case example, you notice that the cap is not that large that we cannot get 21 millimeter from the center line. If you have information in respect to what kind of cap bit we have and that too large, that another parameter that dictate where the center of the front of the probe with respect to weld center can be. And in this case, this would be a good offset. And here in this case, with this sectorial beam set, I could cover the bottom bevel with these parameters. So in this scenario, I come and rename my beam set. I can just rename the beam set and say bottom bevel coverage. Excellent. Now I need to think about how to cover the top bevel. In this case, what I can do, because most of the parameters I'm going to use with the same, I can clone this beam set. So it will create another copy of the same beam set. And then to just make sure that it's not getting color-wise confusing, I can choose a different color here. And then I need to use the lower apertures after a skip to cover the top bevel. So here I increase the skip to 2. And then what I will do is that I will go back to use apertures toward the beginning and toward the lower apertures of the probe. And you notice that as I do that, after skip, I start to come to the point that here seems like what happens is I can easily now cover the top bevel. Maybe I can go slightly lower to start element of 7. And now what I have, if I for a second just turn off the previous one, you will see that now with my angles that were between 50 and 70 still, by choosing the smaller part of aperture, I can now cover the top bevel. And now I'll rename this to top bevel coverage. So this will be the extent of my technique at this point that I'm happy with, that I covered both top bevel and bottom bevel with angles between plus minus 10 from normal to the bevel. But one issue, sort of, not issue, about this beam set, about this technique is that I utilize 2 different sectorial beams or 2 different groups to cover this weld fully. And this means that I will need for my inspection to have 2 calibration, 2 sets of data. There is another way that this can be more efficient, and that would be by utilizing linear spread beam set or compound scan. So again, if you refer to previous videos that explains compound scan, you would probably know the advantage of using compound scan as compared to sectorial. But I'm going to review that briefly here. The difference between the compound scan and sectorial scan is that for the case of sectorial scan, all the beams that we choose will be generated by a same aperture. But when we go to compound scan, we can choose our different angles to be generated by different apertures. For instance, here, if I come and in my compound scan, and I'm just gonna change the color to green so you can see it easier. I go to the same min and max angle, 50 and 70. But then you'll notice that in terms of options, I have the option to choose the first element and end element, which in this case I chose 64, which is the last element of the probe. And then we can choose aperture element size. If I change this to 16, for instance, what you notice happened here is that now the beams that I have, which is 50 to 70, 20 beams, are now being generated by different apertures in the probe. Essentially, what it means is that we gave different apertures in the probe a task to create different beams with the constraint that the last beam will be generated by the last aperture and the first beam will be generated by the first aperture. And in this case, now you will notice that we basically uh, expanded the range of our beams. It is one group, but now these beams are way spread out with respect to each other. So to make it a little bit easier to look at, I'll turn off the previous sectorials, and here I can also still choose to use 0.5-degree increment. And what you will notice now is if I turn on this option here, which is highlighting the beams, as you move this highlighter, all information with respect to the beam that is being generated is presented here. So the information that we have is what aperture actually is generating the beam, what is the angle of the beam, what is the near field, or uh, basically what is the incident angle in the piece. And what I want you to pay attention is that as I move through these beams, first you notice what angles we have, and also notice what aperture is being used. So for first beam, which is a 50-degree that I chose, is generated by the first 16 element because I chose the start element to be 1 and I chose the aperture to be 16. Now, if I keep moving, you notice that now I'm in the next beam, which is 50.5. But this beam is now being generated by aperture from 2 to 17. If I keep moving, what you will notice here is that the angle, as angles increase, also the aperture that's creating those beams are changing. And also you will see that as this line is moved and the exit point on the probe moves toward the top. And also you can notice that you can easily see what beam is hitting the weld bevel. And actually that information is also here, is that whatever intersection angle we have between the beam and bevel is here. And ideally you want to be close to 90. And here, for instance, for this beam, you see that's 85. So as I move, please pay attention to moving of the aperture and change in the information of refraction and intersection of the bevel. But ultimately, because the angles are 50 to 70, and I have a coverage from the top has and bottom has and everywhere, it ensures me that I covered the bevels properly. Now, the advantage that I gained here by using a compound scan was that instead of having two different beam sets, I can cover this weld and inspection with only one beam set. I can give this whole technique a name, 5L64 A12 probe and SA12 N55S. And in general, because for the welds we do two-side inspection, I can call this skew 90. And what I can do, I can clone this whole group and then use this option here to just move it on the other side. And I just give it another color to be easier to look at. And now you will notice that this will be the inspection technique that I'm happy with and have all it's very efficient to cover these bevels from both sides with using compound scan. And info with respect to this is already going to be in my report. And all the information with respect to piece, respect to weld, and dimensions, the technique that is being used, and parameters are already stored here. So thank you for your attention and hope to see you in the next videos.